represent mathematically. There exists a closed form solution, or there exists an equation for a circle, right? So if I ask you to draw a circle, you can easily draw it. In the similar way, if I ask you to identify a circle from an image, you can easily do it, because you can use the equation of the circle to identify it, right? What about the other one, a tree? If I ask you to draw a tree, you can draw different trees, but we want a program to draw a tree. That is not that easy, because we cannot represent a tree with an equation, right? So there is no closed form representation or a mathematical representation for a tree, but we can come up with some kind of empirical solutions. So in these kind of problems, we need machine learning algorithms, right? If it is not possible to represent something mathematically, or if there doesn't exist a closed form solution or analytical solution, then you can use machine learning algorithms. So these algorithms will try to come up with some kind of empirical solutions, right? So if I want a machine learning algorithm to learn a tree, then I have to show my algorithm a large number of trees, because the algorithm has to learn what is a tree. But for a circle, you don't need to learn it, because you know what is the equation of a circle, right? Once you know the equation of a circle, with the center and radius, you can draw circles of different radius, right? So, but still you can also use a machine learning method to draw a tree, but the problem is you have to show a large number of circles to the algorithm. The algorithm has to learn what is a circle, and that is very expensive, right? So collecting data is not that easy, right? And if you want to use a machine learning algorithm, you have to make sure that you have a large number of samples for the algorithm to learn. Otherwise, machine learning approaches will not work, right? So if there exists a closed form solution, then it is always better to use traditional approaches. But if it is not possible to represent your problem using an analytical, using a closed form representation, then we have to come up with some kind of empirical solution that you can do with machine learning algorithms, right? Yeah, the term machine learning was coined by Arthur Samuel. Okay, so this is what we do with the learning, right? With the learning, we are trying to find useful abstractions or concepts that describe the world. So if you look at this screen, you can see some pictures of lion versus other animals that look like lion. So when you develop a machine learning algorithm, you have to make sure that your algorithm can differentiate between these two things, right? Even though these objects, these animals looks very close to lion, this has a different set of features, right? When we develop an algorithm, we have to make sure that our algorithm will be able to differentiate between the lion and the other animals that we use to classify, right? So these are some examples where you can use machine learning and you can use the traditional approaches. So you can see 4 different images. In the first image, see what I want to do is to write a program that can identify all the circular objects. Right. This is what I want to do. This is my input image, and from this image, we have to identify all the circular objects. So whether you need a machine learning algorithm to do it, you don't need a machine learning algorithm, but you can use a machine learning algorithm. But if you use a machine learning algorithm, you have to train the algorithm. You have to develop a model by showing a large number of samples. That is expensive. Since all the objects that I want to identify are of circular nature, I can use a traditional approach like a Huff transform to do it, right? And in this case, we want to identify all these buttons. So if you look at the object, you can see that all these objects are of circular shape. So without a machine learning approach, you can do it. But if you look at the other 2 pictures, this is more complex when compared to the images in the left side, right? So see, from these images, we want to find the 2 mates. Our input is an MRI images, and in some of these images, you can find some kind of abnormalities. So we want to find all the images with abnormalities. That is one thing. And in the other one, we want to find the face. The program should be able to extract the human face from these images. So human face you cannot represent mathematically, right? So in those cases, so we have to train a model using machine learning algorithms, and the model should be able to differentiate a human face from other objects, right? In this case also, so if our objective is to identify a tumor from an MRI images, so we have to show a large number of samples to the model, and the model should be able to differentiate the tumor from the non-tumor images. So for these two problems, you have to use some kind of machine learning algorithms, but the other cases, a machine learning algorithm is not a mandatory. You can use the traditional image processing approaches to do it, but you can always solve these problems with the machine learning algorithms also. But that is a little bit expensive, so you have to do the training. Training is not that easy, right? So you need a large number of samples, and if you are using a supervised approaches, then you have to label it. Labeling is also very expensive. So wherever you can use traditional approach, it's always better to use the traditional approach. And if it is not possible to use a traditional approach, then you can go for a machine learning approach. Is it clear? Any questions? Okay, so if you look at the machine learning literature, you can find a large number of algorithms like logistic regression, support vector machine, random forestry and all. So in the next 2 hours, we will be discussing only about artificial neural networks. So artificial neural network is one of the popular machine learning algorithm. So we will start with the basic neural network, and then we will come to artificial neural network. So you know that at present the most popular deep machine learning approach is deep learning. So tell me why deep learning is so popular, and so first you tell me what is deep learning and why deep learning is so popular. So when somebody says deep learning, usually they refer to an artificial neural network that has a large number of layers, right? So the deep means the deep represents the depth of a neural network. Usually a neural network that is having a depth of more than 3 are considered as a deep neural network, right? So what is the advantage of a deep neural network? So probably you will be familiar with a neural network, right? So a neural network has a neural network composed of neurons, and this is organized in the form of as different layers, right? So what is the advantage of increasing the number of layers? No, learning rate is something like a hyperparameter. You can use a small learning rate or a large learning rate. What about the layers? What happens when you increase the number of layers, or what happens when you decrease the number of layers? Not parallel processing. When you increase the number of layers, you are making your model more complex, right? How the model becomes more complex? More number of neurons means more parameters, right? More parameters means more complexity, right? More complex means your algorithm's learning capability will increase, right? So if you increase the depth, then your model becomes more complex, right? So deep learning usually refer to deep neural networks. So if somebody says that I am using a deep learning algorithm, that means he is using a deep neural network to solve the problem, right? And the neural networks are basically inspired from biological neurons. That we will discuss in the coming slides. So here you can see a shallow neural network and a deep neural network. In this image, you can see a neural network with 3 layers, right? If you consider input layer also as a layer, we have a neural network with 3 layers. If you look at this one, you can see that our neural network has 5 layers. So when you increase the number of layers, the complexity of the neural network will increase. And when you increase the complexity of a neural network, see, it can learn more things, but you have to make sure that you have more data. If the amount of data is very less, then you cannot increase the complexity. That would lead to overfitting. That we will discuss in the coming slides. Okay, so why people are using deep learning? You know that deep learning, if you look at the literature, you can see that at present deep learning is the most popular machine learning approach, right? Why everybody is running behind deep learning? I think probably many of you will be PhD students, right? That you can use other machine learning algorithms also, right? Where? Deep learning, we don't need to do automatic feature extraction. Who will do feature extraction in convolution? I think when you say deep learning, you are referring to a convolutional neural network. Is it right? And who will do feature learning in convolutional neural network? Which layers? The traditional ANN also has layers, right? Okay, you'll see. See, you can see a graph here. So in the x-axis, you can see this is the amount of labeled data, and this is the model performance. And we are comparing different. Here we can see the performance of different types of neural networks and convolutional machine learning algorithms. So you can see that when you increase the amount of data, the performance of every machine learning methods will improve, right? Why the performance of machine learning methods improve with the increase in data? Because you will be able to extract more features, right? So the performance of the machine learning methods will increase with increase in data. But after certain level, you can see that these methods will saturate, right? And you know that if you look at the traditional machine learning approaches, see almost all these methods learns based on the handcrafted features, that is the features that you provide. Say if I want to differentiate between two flowers, say flower A and flower B, with the traditional approach what we do is we will extract the features from flower A and we will extract the features from flower B. Assume I want to do this classification based on 10 features, then I will extract you need the help of an expert also in this case, right? Who will extract the feature? So we need the help of an expert. So if you want to do a classification of two different flowers, and you need the help of an image processing expert to look at the features, and based on these features we are going to do the classification, right? So assume the expert identified 10 features, then we will be doing the classification based on these 10 features, right? And now we have the data. So if you increase the amount of data, then we will be able to extract those features properly. And now assume that we have 10,000 samples and we have 20,000 samples. So this may not make much difference in extracting the features, right? So the performance will not increase much. But when you have 10 samples and 100 samples, there is a difference. With 100 samples, you can extract the features much better. But after reaching a certain level, the performance of these models will saturate, right? So this is the case with the artificial neural networks also. Artificial neural networks also you are giving the features as an input, right? So why the performance of convolutional neural networks keep on increasing? So in the case of convolutional neural network, we have convolutional layers. So we use a neuron with a convolution operator. So there the advantage is the convolution operation can extract the features. So if you have more samples, you can increase the number of layers. The more the number of layers, the model can extract more features. When you increase, when the model is able to extract more features, then the model can perform much better. So that is the reason why the performance of convolutional neural networks keeps on increasing when you increase the number of samples, right? And this is the reason why most of the people use convolutional neural network to solve their problem. And this works if you have a large number of samples. The other advantage is with a convolutional neural network, you don't need to extract the features. It will automatically extract the features. With the traditional machine learning algorithms, we need the help of an expert to extract the features. That means the handcrafted features, right? So we have to extract the features, and the classification or the segmentation is based on those features. With the CNNs, you don't need to do it. That means your work is very less, right? You don't need to do anything. Collect the data, design a network, everything the CNN will do. What people do is they will simply play with a number of layers and all those kind of things, right? That is why most of the people wants to use CNN instead of machine learning. But if you want to use the traditional machine learning, then you should know something about your samples. You should know what features has to be extracted, right? With CNN, you don't need to do those kind of things. And even if you are using the popular frameworks like Keras or PyTorch, all those things are, most of the architectures are available as built-in architectures. So your work is very less. What people try to do is they will use some architecture, they will get some data, just do this trial and error approach with different adding and deleting the layers and get the results. That is what most of the people do, right? So as a computer science person, we should come up with a more efficient architecture. That is what actually we have to do. That most people are unfortunately not doing, right? Okay. Okay, any questions? So you have some idea about, so I try to explain the difference between the traditional machine learning approaches, artificial neural networks and convolutional neural networks. Both ANN and CNN are neural networks, but the difference is in the case of convolutional neural networks, we use convolution operator, and that is not there in ANN. This is clear, right? If you have any questions, you can always interrupt me and you can ask questions. What will be the ideal? No, if you have more samples, that is always better. This is like see, if you get millions of samples, then you can see. See, if you take the example of handwritten digits, so different people write a particular digit in different ways, right? So if you get more samples, the model will be able to see the more ways of writing one particular digit. So the generalization error will come down if you increase the number of samples. No, the saturation is in the case of the traditional ML algorithms. But CNNs, in most of the cases, the performance will keep on increasing if the model is able to extract. But this again depends on the complexity of your problem. See, if your problem is of less complexity, even with a less number of samples, your model will work. If your model is, if the problem that you want to solve is more complex, then you need more samples. Okay. So when you design a machine learning model, you know that if you want to work with the machine learning algorithms, you need data, right? Usually we divide the data into train, validation and a test, right? What is the purpose of train data? What do you mean by training a model? Yeah. So when we do the training, we are trying to find the optimal values of the parameter. If you take the case of if you look at a neural network, what are the parameters in a neural network? I assume that you have some idea about neural network. So what are the parameters in a neural network? Weights and bias. Weights and bias are the parameters. So we use the trained data to find the optimal values of these parameters, right? And what about the validation data? So validation and test data are used to evaluate the performance of the model, right? So we are developing a model. To develop a model, we have the trained data, right? And to evaluate the performance of the model, we use the validation data and the test data, right? So both validation data and test data are used to evaluate the model. Then what is the difference between validation data and test data? So how test data is different from validation data? Then why we need test data? why can't you test it with validation? Yeah. So see, the difference between test data and validation data is test data is unseen, totally unseen. The model is not seeing the test data at all. But validation data is not unseen data. In the sense, we use validation data to fine tune the hyperparameters, right? So in that sense, validation model is seeing validation data. That means we use validation data also in the process of building a model. So, but the test data is totally unseen, right? So that is why we need the test data to evaluate the performance of the model. But while developing a model, we need the validation data also, right, to fix the hyperparameters. That is the difference between train data, validation data and test data. So we use train data to build the model, and we use validation data and test data to evaluate the model. And to fix the hyperparameters, we use the validation data. In that sense, the model is seeing the validation data, and test data is totally unseen data. So usually the thumb of rule is, see, 80% of the samples usually we use to build the model. That means 80% of the samples will be there in your train set, and the remaining 10%, 10 you can put as a validation and the test. But that again depends on the developer. Even you can use 70, 15, 15 and all. That depends on how many samples you want to include in the train set. Usually we need more samples in the train set. Why? Why more samples we will put in the train set instead of test set? Because you have to see, you have to build the model from the data. You need more data to build the model, right? If you put less number of samples in train and more number of samples in the test, then you have very less samples to build the model, right? The model should, to build a model, you need a large number of samples. Model should, your algorithm should see all possible, what are the possible cases. If you take the example of this 110 digit, see, the way I write a particular digit, say 2, is different from the way you write 2. So model should see all possible ways of writing the 2, right? Then only the model will be able to generalize. So you always need a large number of samples to develop a model. That is why 80% we use for training, or 70%, that depends on the you. You can also say that validation data is the developer's test data. So if I want to develop some machine learning model, so you just assume that you people are developing the model for me. So I will not give all data to you. I will keep some samples with me, because I don't know whether you people will cheat me or not, right? You can fabricate some kind of thing and some output, and you can show it to me. So I always keep some 10% of the samples with me to test the model that you develop, and I will give this 90% to you. And you have to develop the models using this 90%. So what you will do, you will divide this data into, say, train and validation, or you can also develop divide this data into train, validation and test, and you use some percentage of these samples to develop the model and some percentage to validate. This is how you develop it, and then you will give the model to me, and I will test your model on my test data. So my test data is totally unseen. Your model is not seeing my test data, right? Okay, so this is clear, right? So we need data to develop machine learning models. So we use an algorithm and we have the data. So what we are getting as the output is a model, right? You know the difference between an algorithm and a model, right? So you can use any machine learning algorithm. See, we have we need the data, and you have to choose an algorithm. The algorithm can be, say, linear regression, logistic regression, SVM, or artificial neural network. So you have to select an algorithm, and we have the data. We use the data to develop a model using this algorithm, right? And to develop a model, you need the train data and the validation data, and we test it on the test data. The test data is the unseen data, right? And yeah, so there is something more we want to discuss. Okay, this I will skip now, and I will talk about this overfitting and underfitting. These overfitting and underfitting are commonly used terminologies in machine learning. So whenever you develop a model, you have to make sure that your model is not underfitting and the model is not overfitting, right? So what is underfitting? So when can we say that our model is underfitting? So you have to develop a model. I'll give the data, and your model is underfitting. What does it mean? Use it. Yeah, underfitting means your model is not able to learn the data. So we have some samples and we used an algorithm, and our algorithm is too simple to learn the data, learn the problem. Right. In this case, what happens is we can call this situation as underfitting. So you can see an example here. See, so these blue dots are my data. So these are my samples, these blue dots, and these samples are generated from this green curve. Right. So this is the ground truth. This green curve is the ground truth, and we are generating some samples from this green curve. And when we generated these samples, some noise is also added to the samples. Right. That is why these blue dots are not exactly on this green curve. Right. And you have to develop a model that has to come up with this green curve. So the expected output is this green curve, right? Your input is these blue dots, and now I am going to start with a simple model. So a simple model is a line. I am starting with a simple model, and I use this data, and this is the output that I am going to get. I got a line. So you can see that this line is not fitting these dots, right? So in this case, you can call that the model is underfitting, because my model is too simple to represent the samples. So if the model is underfitting, then what is the solution? You have to increase the complexity or capacity of the model. So how will you increase the capacity? Yeah, adding more variables. So you will add more variables to increase the capacity. In this case, see, I use a polynomial of degree 1. So instead of a polynomial of degree 1, we are going to use a polynomial of degree 4. Right. Now you can see that when we increase the capacity of the model, see, we got a curve that is very close to this green curve. Right. And now see, when I increase the capacity, I found that the model is fitting the data very well. So why should I stop here? I can increase the capacity further. So from degree 4, I increase the capacity further to degree 15. When I increase the capacity to degree 15, this is what I got. My model is exactly fitting all those blue dots. But this is not what I want. What I want is this green one. Right. So this is what I got. Right. So this is called overfitting. So what happened here is, so you can see that these blue dots are not exactly on this green one. There is some noise. So the model learns this noise also. Right. So in this case, my model is overfitting the trained data. So the generalization error will be more. So when you develop a model, you have to make sure that the model is not underfitting and the model is not overfitting. So how will you check it? Check whether your model is underfitting. What you have is trained data and the validation data. With the trained data and validation data, how will you check whether your model is underfitting or not? No, you are developing a model. You just assume that you are developing a model using neural network. You have the trained data and the validation data. So how will you check whether your model is underfitting or not? You can compute the train error and the validation error, right? So when underfitting happens, then what will be your train error and validation error? Whether it will be high or less. When train error is high and the validation error is high, that means your model is underfitting. So you can always, you have the train data and validation data with you. So you can always compute the train error and the validation error. If the train error and validation error are high, that means your model is underfitting. So what we will do, we will increase the capacity of the model or the complexity of the model. When you increase the complexity of the model, what happens to this error? Error will come down, right? So now assume that we are keeping on increasing the capacity. So if you increase the capacity to a large amount, that means like degree 15, then what happens to this train error? Train error will reduce very well, because our model is fitting the train data very well. The train error will come down. So what about the validation error? It starts increasing. So when you start increasing the capacity of your model or the complexity of your model, both train and test error will come down, but after a certain point of time, you can see that the validation error starts increasing. So that means your model starts overfitting. So there you have to stop, right? So that is how we find the optimal capacity. So we always starts with a simple model, right? So when we develop a model, we always starts with a simple model. Why we always start with a simple model? Why can't we start with a complex model? Yeah, simple model means less number of variables. The training will be faster, and if you want to train a model, so you have to load your model to the memory. So the memory requirement will be less, right? So when you train something, you need both the train data and your model in the memory, right? Right. So we always prefer a simple model. If a simple model is giving you good results, then that will be really good, right? So because these models need only less amount of memory. A complex model means more variables will be there, and the amount of memory that is required will be more, right? So if you can solve the problem with a simple model, then that is always good. That is why we always start with a simple model, and we slowly will start increasing the complexity. If the simple model is not sufficient to solve the problem, then we will go for a complex model, right? So we gradually increase the capacity, and we will see what capacity of this model will solve your problem, right? That is how we develop the model, right? Is it clear? No. So you can see it here, this the capacity and the error. So this red one is the validation error, and this blue one is the train error. So when you increase the capacity, you can see that the training error will come down, and you can see that the training error will go very close to 0, because we are using a very complex model, right? And the validation error will also come down, but you can see that after certain level, the validation error starts increasing. That means the generalization error will start increasing. So we always want a model with a less amount of generalization error. It is not but of course when we stop here, the train error will be more, but we don't need to bother about it. So we always prefer a model with a less generalization error. It is not a less train error, right? The train error and the validation error both should be less. That means the generalization error should be small, right? That should be the focus when we develop a model. Is it clear? Okay. So these things are common to all the models. Whatever algorithms you use, whether it is artificial neural networks or support vector machine, we will do the same thing. So you have to make sure that your model is the generalization error of your model is less. Okay. Now we will start with these artificial neural networks. So artificial neural networks are considered as very powerful machine learning models, especially as I told. At present, CNNs are the state of the art, most powerful machine learning approaches. So, you know that these artificial neural networks are basically inspired by the working of biological neurons. So, in the next slide, I will try to briefly explain how a biological neuron works and how it is, how this McCulloch-Pitts developed an artificial neuron based on this biological neuron, right? So another advantage of this artificial neural network is, say, the universal approximation theorem says that with enough hidden layers, you can approximate any functions with a neural network. That looks something interesting, right? So whatever be the function, you can approximate it with a neural network, provided we have enough hidden layers. That shows the power of the neural network, right? So here you can see the anatomy of a biological neuron, right, or a nerve cell. You can see that the nerve cell has these dendrites. So these neurons collect the information from other neurons or from the sensory organs through these dendrites, and this will be processed in the cell body, and based on the strength of this operation, a signal will be generated, and this will transfer to the next neuron through these axons. And you can see that there is no physical connections between these two neurons. So so the communication is through some kind of electrochemical reactions, right? So inspired by the working of biological neuron, McCulloch and Pitts developed a simple mathematical model of biological neuron, and they published a paper based on their observations. And this paper, published in 1943, is considered as a classical paper in artificial intelligence and neural network. So I will briefly explain this paper, and then we will see how we can use a simple artificial neuron to solve some simple problems, like designing a logic gate and all. So this is how their mathematical model look like, and this is considered as the first mathematical model of a neural network. So here you can see a biological neuron and a corresponding artificial neuron. So a biological neuron will take inputs through these dendrites. So we have inputs here, right? And so here we have this is a cell body of the artificial neuron. Inside the cell body, what we do is we will compute the weighted sum. See, associated with every inputs, we have a weights, and this weights corresponds to the synaptic strength of strength in artificial in the biological neurons. So associated with every inputs, we have a weights, and in the cell body, we will compute the weighted sum. How will you compute the weighted sum? I1 W1 plus, if I1, I2, etc. In are the n inputs, we will compute the weighted sum by I1 W1 plus I2 W2 plus etc. In Wn, right? And then this and then once we compute the weighted sum, we will decide the output, and this output is decided by the strength of the weighted sum. So if this weighted sum is greater than a threshold, then your neuron will fire, otherwise your neuron will not fire. So you can write this as a, say, output is equal to 0 if the sum is less than t, or output is equal to 1 if the sum is greater than t. Or you can, so this operation you can write as a step function also, y is equal to f of sum, where this f is a step function, right? So you know how a step function works, right? So you will get an output, this is the step function, right? So if your weighted sum is greater than a threshold, you will get an output, say output will be 1, otherwise it will be 0. So you can say this step function is the activation function, right? So we have n inputs, and first we will compute the weighted sum, and if the weighted sum is greater than a threshold, our neuron will fire, otherwise the neuron will not fire, right? So this is the model that they proposed in their paper. So this model is very simple, right? So this model is very simple, but even though this model is very simple, you can design simple operations like this logic gates. Logic gates you can easily implement with this model. So you will see how can we implement the logic gates using the McCulloch-Pitts model. Okay, so we will try to implement an AND gate with this MP model. You know how an AND gate work, right? So you just assume that we are going to design an AND gate with the two inputs. So what is the condition to get an output 1? You know the truth table of the AND gate, right? So when both inputs are 1, we will get an output 1. So now you have to use this MP model to design an AND gate, right? So this is the model. So we are going to use a single neuron. This neuron will take two inputs, A and B, right? And it should output is Y, and y is 1 when a and b are 1. In all other cases, you should get an output 0, right? So what are the parameters in this model? WA, WB and T. These are the parameters. So you have to find what values of WA, WB and T will make this neuron an AND gate. Right, how will you find it? So this is a simple neuron. Right, we have a neuron with 2 inputs, right, and you have to make this neuron an AND gate, right. So making this neuron an AND gate means you have to find appropriate values of WA, WB and T. So what value of WA, WB and T will make this neuron an AND gate? If you use a different values of WA, WB and T, you can convert this neuron to an OR gate or an AND gate, right. So now we will see how will you find the values of WA, WB and T, right. So when both inputs are 0, what is the expected output? 0. That means 0 into WA plus 0 into WB. This is a weighted sum. So this weighted sum should be, whether it should be greater than T or less than T. Greater than T means the neuron will fire, you will get output 1. Less than T means output is 0. When both inputs are 0, so 0 into WA plus 0 into WB, this should be less than or equal to T, right? Or you can write this as a T should be greater than or equal to 0, right? Now when A is 1 and B is 0, what is the expected output? 0. That means 1 into WA plus 0 into WB should be less than or equal to T, because the neuron should not fire, right? Or you can write WA should be less than or equal to T. Now when A is equal to 0 and B is equal to 1, what is the expected output? Again 0. So 0 into WA plus 1 into WB should be less than or equal to T, or you can write that WB should be less than or equal to T. And when both A and B are 1, we will get another equation, WA plus WB should be greater than T. Now we have a system of equations. You can solve this system of equations to find the value of WA, WB and T. But of course you will get multiple solutions, but that is still okay as long as it works here, right. So in this case I set the value of WA and WB as 1. So you can see that WA, T should be greater than or equal to 0. So I set the value of T as 1.25, 1.5 is greater than 0, and WA and WB should be less than T. I set the value of WA and WB as 1, and this is less than 1.5. And if you add WA plus WB, this should be greater than T. WA plus WB is 2, that is greater than 1.5. Now if you use these values of the parameters, that is WA is equal to 1, WB is equal to 1 and T is equal to 1.5, this neuron will act as a AND gate, right. Right. Similarly you can design OR gate, right, or NAND gate. Right. So you have to solve a system of equations. So you know that see, the idea is very simple. See, the artificial neuron is so simple in this case. So the concept is very simple, but you can design logic gates. So their idea was to design a computer using artificial neuron. So if you can design logic gates, you can also design a computer. So that was the motivation behind this work, right. So, however, one problem with this approach is, this approach is not automated. So, you have to find the values of the parameter, but to find the values of the parameter, you have to solve a system of equations. So, in this case, the number of inputs are very less, the number of variables are less. When the number of variables are more, then it becomes more difficult for us to find the optimal values of these parameters. So, this is not an automated approach. So, we cannot call this as a machine learning approach, because we should find all those parameters automatically. From the data, the algorithm should be able to come up with the parameters, right. So, here we have to solve a system of equations to find the values of parameter. So, this is one drawback of this approach. The other approach is, this algorithm work only if the data is linearly separable. So, what do you mean by linearly separable? Yeah, you can separate the data with a line. So, this will not work. See, for AND gate or OR gate, this will work. For XOR gate, it will not work. because you cannot separate these two classes with a line. Right. So this MB model will work only if your data is linearly separable, and this is not an automated approach. So to solve some of the problems of this MB model, Frank Rosenblatt come up with a modified version of MB model called Perceptron. So the difference between MB model and the Perceptron is an automated algorithm. So this algorithm automatically find the values of the parameters. You don't need to solve a system of equations. So you'll see what are the differences between the Perceptron and the MB model. So see, the one difference between the Perceptron and the MB model is he introduced something called a bias. A bias is nothing but the threshold, because in the neural network, when you talk about neurons, you always talk about something called bias. So what is this bias? So the term bias was introduced in the literature by this Frank Rosenblatt. So what he did is, see, this is what we do with the MB model, right? We will compute the weighted sum, and if the weighted sum is greater than t, then the output is 1, otherwise it is 0. So he moved this t to the left side of the inequality, and he called it as the bias. So what the bias is nothing but minus t. Or you can say that bias is a measure of how easy it is to get the perceptron to output 1. This is one modification that he did. This is just a say an adjustment to solve these equations in a faster way. So there is nothing new in this one. And the other thing is he also introduced a learning rule to find the values of the parameters. And even this learning rule is not entirely new. So he took this learning rule from the book of Hebb. So this is how this learning rule look like. So see, our neuron has 3 parameters now, right? So if you look at the AND gate, the W's and the T's. So W and the bias are the parameters. So what you can do is, we will initialize these parameters randomly, and then we will update it. This algorithm is an iterative algorithm. So we initialize it randomly, and after every iteration we will update the value, and after, if your problem is linearly separable, it will converge after some time. So we'll look at this learning rule. So this is how these W's are updated. Wi plus 1 is the new value of W. So Wi plus 1 we compute as Wi plus delta W. And this delta W is eta into R into X, where this X is the input. R is the difference between the expected value and the predicted value. And this eta is a what we call, it's a learning rate. We will talk about the learning rate in detail in the next slide. So usually we give a small value of this as this learning rate. And you can see that when the predicted value is same as the expected value, R becomes 0, and our W will not update, right? So if the problem is linearly separable, after a few iterations, the error becomes 0, and your model will converge. In a similar way, we will update B. So this is the learning rule that is used in Perceptron, right? So in this case, what we will do is, so if you want to design your AND gate using Perceptron, see, our model has 3 parameters. So if you go back to this one, so if you want to solve this problem using the Perceptron, what we will do is, we will initialize WA, WB and B. So in Perceptron there is no T, it is a bias. So these 3 variables we will initialize randomly. Then we will update these variables, right, with the help of this iterative algorithm, the Perceptron learning rule, we will update it parameters. So after few iterations, the model will converge. There we will stop. So Perceptron is an automated approach when compared to MB model. MB model is not an automated approach, Perceptron is an automated approach, right? Is it clear? Right. So yeah, so I will discuss an experiment using Perceptron. So what we want to do is, we want to use Perceptron to differentiate between these 2 fluids. So our input is these 2 fluids, but we are not giving an image as an input. Instead, I am going to extract some features from these 2 fluids, and we are going to give it to Perceptron. The features that we are going to consider are the sepal length and the petal length. So I will extract the sepal length and petal length from from this iris versicolor flowers. Both these flowers belongs to the iris family. One is the versicolor and other one is the setosa. So I'll extract the sepal length and petal length from this data and from this data. So you have to collect a large number of samples, say 100 or 200 samples of this flower and 100 or 200 samples of this flower. Then we have to compute the sepal length and petal length. So now our train data is ready. So you can give these features to the perceptron to do the classification. So this is the distribution of sepal length and petal length. So you can see that this is linearly separable. So if you use a perceptron, so after few iterations the model will converge. So perceptron will come up with the separation surface. Right. Is it clear? Okay. Now we will do one more experiment. So in this experiment, see, I am going to use a different flower. Again, both these flowers belongs to the iris family. Here it is Virginica and versicolor. And if you look at the distribution of this one, you can see that this is not linearly separable. So if you try to use perceptron to do this classification, then your model may not work properly because your data is not linearly separable. But again, another thing that probably you might have observed is if you look at the decision boundary generated by perceptron, you can see that this is a small margin classifier. Small margin in the sense, see, your margin is very close to one of these samples. So this is another drawback of perceptron. Perceptron is a small margin classifier. So if your data is not linearly separable, then the error generated by perceptron will be high. You just assume that your classifier is a linear classifier, but it is a large margin classifier. So if your classifier is a large margin classifier, then the error generated by the classifier will be less, even if it is not linearly separable. So this is one problem with the perceptron. So perceptron will always converge if your data is linearly separable. But if your data is not linearly separable, then the error generated by the perceptron will be little bit more when compared to a classifier that is a large margin classifier. So you can see it here. So instead of this margin, if your perceptron generate this margin, these dotted lines, then you can see that that kind of classifier is a large margin classifier. See the difference. See, in the case of a large margin classifier, so this decision boundary should be away from both these samples as much as possible, right? But you can see that if you look at the margin of this classifier, this is very close to one particular class. So margin should be far from both these classes, right? So in that sense, the perceptron is not a large margin classifier. Perceptron is a small margin classifier, but still it will converge if your data is linearly separable. Yeah. So this we can. So to address the limitations of perceptron, Bernard Widrow and Ted Hoff come up with an algorithm called adaline. So this adaline is considered as a base model for most of the current neural networks, because the difference between this adaline and perceptron is the learning rule. In perceptron, Rosenblatt used this perceptron learning rule. In adaline, the learning rule was based on the gradient descent method. So you know that almost all neural network use a gradient descent method to find the optimal values of parameters. So we will see how gradient descent work, and we will also try to come up with this learning rule based on the gradient descent method. Okay, so first I will try to explain this gradient descent method. Then we will generate the learning rule for this neural network. Okay, so in the screen you can see some graphs. So we will take this example first. You just assume that you are standing somewhere here, and we want to reach this point from this particular point. So how will you? So what you have to do is you have to move through this line and you have to reach here, right? So what about the slope of this line? Is it positive or negative? This one. How will you compute the slope? Y2 minus y1 divided by x2 minus x1, right? So you can see that the slope of this one is a positive. So if you want to reach this point from this particular point, then you have to move against the slope, right? So I can write, for this movement I can write an equation like x is equal to x minus alpha into m, where this x is my current position, and I will compute my new position as x is equal to x minus alpha m. So I have to move against the slope, right? So, and we are trying to move against the slope. When we move against the slope, I can take a large step or I can take a small step, right? So what happens if I take a small step? If I take small steps, then what will happen? Or when the value of this alpha is very small, then what happen? Yeah, it take more time to reach this point, right? If you take large step, then what will happen? Less time, but there is a risk. Sometimes we may overshoot this point, right? Right. So we should be very careful with this alpha. So if you take very small value, then you have to wait more time to reach this point, and if you take large step, you may overshoot, right? So you have to, so your learning rate, this is called the step size or the learning rate. It should not be very small or too large, right? So we have to move against the slope, and you have to take some small step, and finally you will reach here. Now assume we are moving through this particular line. How this line is different from this one? Slope is negative, but you can still use the same equation, x is equal to x minus alpha into m, where m becomes negative, so this equation will become x is equal to x plus m. So you can use this equation to move through these two lines, right? Now instead of line, I want to move through a curve. How a curve is different from a line? How a curve is different from a line? Slope is different at a different points. So if you look at this line, the slope is same at every point, right? In the case of a curve, the slope is different at different points, right? So how will you find the slope of a curve? Yeah, you can take the derivative, dy by dx, you will get the slope. So dy by dx at different points will be different. So you can still use the same equation, but I am computing the slope is, my update formula is x is equal to x minus alpha into dy by dx. In this case, this m is same everywhere for the line. Here we will compute dy by dx. So see, assume we are standing here, and we will compute the derivative, and based on this derivative, we will move, right? So if the slope is negative, so in this case, when the slope is negative, we will add this slope. It becomes x is equal to x plus alpha into dy by dx, and we will move through this curve, and our target is this point, right? So what happens when we reach this point? What happens to this slope? 0. When the slope is 0, x will not update. So this is how we move through this curve, right? So we want to find what value of x minimizes y, right? This is an optimization algorithm. This is how the gradient descent work. And now in this case, my y is a function of x. Now assume that we are moving through this particular surface, and here my y is a function of x1 and x2. So we want to find what value of x1 and x2 minimizes y, right? So here we have to take the partial derivative. So our equation will be, see, we have to minimize both, we want to find what value of x1 and x2 minimizes y. So we have to update both x1 and x2. In this case, we need to update only x, right? We want to find what value of x minimizes y. So what value of x we will reach this particular point. This is the global minima, right? Here we are trying to find, we want to reach here. So you have to update x1 and x2. And what is the update formula for x1? x1 is equal to x1 minus alpha into dou y by dou x1, and x2 minus alpha into dou y by dou x2. And you can arrange these partial derivatives in the form of a vector, and you can call this vector the gradient. This is how the gradient descent methods work. So with the gradient descent methods, we are trying to find, see what value of this variables minimizes over y. Right. In this case, we want to find what value of x1 and x2 minimizes y. Right. So we will update both x1 and x2 using this formula, and when we reach the global minima, the partial derivatives will be 0, and x1 and x2 will not update. So when this curve is convex, it always converge. When it is not convex, then or if it looks something like this, then convergence will be very difficult. There is always a chance that we can end up in local minimas. So in this case, there is only one minima, right? That is the global minima. So here you can see that this is the global minima, but if you start somewhere from here, there is always a chance that you will fall in local minima. So for both local minimas and the global minimas, see the derivative is 0. When you fall in local minima or when you fall in global minima, the parameters will not update. So the algorithm thinks that okay, this is the global minima. So and as a result, you are going to get some kind of a suboptimal solution. So but if your this curve is a convex curve, you will always reach global minima, right? Now we will see how can we use this gradient descent method to what is it? Find the optimal values of the parameters. So we will take the same neuron and we will see how can we find optimal values of the variables in a neuron using the gradient descent method. So the gradient descent method is clear to you, right? Okay. Okay. So now I'm taking again the same neuron, a simple neuron. So this neuron has a two inputs, x1 and x2. So w1 is the weight associated with x1, w2 is the weight associated with x2. So the first step is to compute the weighted sum, right? So inside the neuron, first we will compute the weighted sum. So this is how we compute the weighted sum, right? x1 w1 plus x2 x1 w1 plus x2 w2 plus b, where b is the bias of this neuron. After computing the weighted sum, we will give the weighted sum to the activation function, right? So here for convenience, I assume that my activation function is an identity function, right? I am using an identity function as an activation function. So what is an identity function? Yeah, the output will be same as the input in the case if your function is an identity function, right? So here my f is an identity function. So what will be y? Y will be equal to a. Okay. So my y will be equal to a, and now I have a neuron. It will predict y. So how will you check whether the predicted value is same as expected value? So you need an error function to check whether the predicted value is same as a. Either you can write it as y minus a. You just assume that the target output is t and the predicted output is y. So either you can compute y minus t. If y minus t is 0, that means the predicted output and the expected output is same. So here we are going to use this squared difference, t minus y the whole squared. And for convenience, I am going to put this half here. This is just for the convenience of solving this equation. So t minus y the whole squared. So I am computing, this is my error function, t minus y the whole squared. And yeah, so we always need an error function to see whether the predicted output is, how close the predicted output is to the expected output. Okay. Now we want to come up with a learning rule. A learning rule, I am going to use the gradient descent method to derive the learning rule. So what we want to find is what value of w1, w2 and bias minimizes the error, right? Okay. So we will start with some values of w1, or you can write that w1 is equal to w1 minus alpha into dou e by dou w1, right? So we are starting with some point, right? We want to find what value of w1 minimizes the error. So here we have three parameters, W1, W2 and the bias. So we want to find what value of W1, W2 and bias minimizes the error. So this is same as what we discussed earlier. See here. Here we try to find what value of x1 and x2 give the minimum value for y. This is same as what we are discussing here. So we want to find what value of W1, W2 and B minimizes the error. So we can write this this W1 as W1 is equal to new value of W1 is equal to old value of W1 minus alpha into dou E by dou W1, right. So this dou E by dou W1, again you can expand, you can apply the derivative chain rule here. You can see that E is a function of y. So you can write dou E by dou W1 as dou E by dou y into dou y by dou W1. Again you can see that this y is a function of A. So you can apply the chain rule one more time here. So you will get dou E by dou W1 as dou E by dou y into dou y by dou A into dou A by dou W1. Now we will solve this one. So what is dou E by dou y? See, E is half of t minus 5 whole squared. If you take the derivative here, you will get this half and half will cancel. That is why we put this half here. So you will get minus of t minus y. And dou y by dou A is 1 because y is equal to A. And dou A by dou W1, so you will get x1. Right. So now if you look at this dou E by dou W1, you will get minus of t minus y into x1. So the new value of W1 will be W1 plus alpha into t minus y into x1. So we will now we got a weight update rule for W1. Similarly, you can compute W2 and B. So now we have a weight update rule, right. So we will initialize the neural network with some random values and we will update these values using this weight update rule. So this weight update rule is based on the gradient descent method. So we want to find what value of W1, W2 and B minimizes the error, right. So in all modern neural networks use this gradient descent method to find the optimal values of the parameters. But if you want to use gradient descent, you have to make sure that your error function is differentiable. Your error function should be differentiable, otherwise you will not be able to do it. Here in this case, so when we have a large number of samples, this E is nothing but the mean squared error. Now I explained this with only one sample, but you have n number of samples. The error that we compute is the MSE, the mean squared error. This is one criteria. Your error function should be differentiable. The other thing is your activation function. Here we used identity function as an activation function. The activation function also should be differentiable. Otherwise, you will not be able to use the gradient descent method. You have to make sure that the error function and activation function are differentiable. Right. Okay. Is it clear? The perceptron. Yeah. In perceptron, if you look at the perceptron, so what was the activation function that that was used in perceptron? Which activation function was used in perceptron? Yeah, it is a step function. We used a step function as an activation function. So step function is not a differentiable function. So you cannot use step function as an activation function with a gradient descent. In this case, we used an identity function as an activation function. Identity function is differentiable. So perceptron learning rule is one way to update the parameters. This one is so there we have a learning rule, perceptron learning rule. Here again we derived a learning rule based on the gradient descent. But you can assume this is a general framework where you can use any error function and activation functions. The only condition is these two functions should be differentiable. In this case, we used an identity function as an activation function and the MSE as a loss function or the error function, but you can use other functions, but those functions should be differentiable. Right. So now if you compare these two methods, the adaline and the perceptron, you can see that this is a large margin classifier. This adaline is a large margin classifier when compared to the perceptron. So here you can see it. So this is the same experiment, and if you look at the suppression surface generated by adaline, you can see that this suppression surface is much better than this one. So this is very close to this particular class. So both perceptron and adaline will converge if the data is linearly separable. You don't need to bother about it. Both will converge. But if your data is not linearly separable, then the error generated by the adaline will be lesser than the error generated by perceptron, because this is a large margin classifier. The other one was a small margin classifier. Right. However, one drawback of this adaline is, see, we used an identity function as an activation function. So, so the output will be A. The output of the adaline is the weighted sum. But you just assume that you want the output as a class, a 1 or 0. Then again you have to apply a threshold on this on the predicted output to convert the predicted output to a class value. There the problem is the output can be minus infinity to plus infinity. So converting it to a class is not that easy, since the output is not bounded. So the output of perceptron is bounded. So output of perceptron is either 0 or 1. But the output of adaline is not bounded. It is minus infinity to infinity. So you have to apply a threshold and you have to convert the predicted output to a class. So this is one drawback of the adaline. Right. So what is the solution? How can we solve this problem? Output is not bounded in this case. So you can use a function that is bounded. Right. And another problem with this adaline is, see, the activation function that we used is a linear activation function. So you cannot design non-linear classifiers. So in practice, most of the classifiers that we are using are non-linear classifiers, because linear classifiers are simple classifier. You cannot solve complex problems with a linear classifier. Even if you make even if you compare this linear classifiers, still it will be a linear classifier. That means if you create a neural network with linear neurons, it will be still linear. Right. So this adaline is a linear classifier. Of course, perceptron also do the same thing. So we are more interested in a non-linear classifier, because if your data is not linearly separable, then none of these linear classifiers will work. Is it clear? Any questions till this point? The error function, you cannot always assure that it is a complex, it is a convex one. If it is not convex, then you may struck in local minimas. That is, usually this will happen in neural network, but there are certain ways to escape from local minimas. So those algorithms are there, but that will not be discussing in this lecture. No, but usually these error functions, see, your error function is a function of millions of variables. It is not 1 or 2 variables. So here we consider only x1 and x2, right? So usually your inputs will be, your error function is a function of a large number of variables. So assuring that this function is a convex function is very, it will not be a convex function in practice. So that is why your random initialization is also very important. So if you repeat this experiment multiple times, you can see that every experiment is not may not give you the same error value, because if you are very close to the global minima, your algorithm may converge very fast. But if the values that you initialized are far away from the global minima, then your algorithm may take more time, and there is always a chance that it will converge to a local minima. In that case, you will get suboptimal solutions. Right. So now we will see how will you make this neuron a non-linear and how can you design a non-linear classifiers. These all are fundamentals with the traditional neural networks only. So whether we should take a break now? Okay. So after the break we will discuss how can we make it non-linear and how can we introduce convolution to a neural network.
Everyone can have breakfast.
This is something that I missed. So we discussed about this train data, validation data and test data, right? So you also know that usually we need a large number of samples to develop a model. So what if the samples are less? So you just assume that there is no way to get more samples, but we have a reasonable number of samples that is not that high, but that is still enough to develop a model. So in that situation what we can do is you can also do a cross validation, a k-fold cross validation to evaluate the performance of the model. Otherwise there is a chance that your model can be biased towards your test set if you are doing only one experiment. You take a simple case, so assume that we have 10 samples to design a model. Of course 10 samples is a very small number, but just to explain the concept still I can do with this 10 model. So what we want to do is we want to design a model that can classify this apple and orange. So assume that we have 7 apple and 3 orange. So our data is imbalanced, so it is highly imbalanced, right? And when you create this train and validation, we always create this train and validation randomly, right? So right, we use the random function. We have 10 samples, so we use a random function to create the train and validation, right? So in this case it will work in your lab, but your model will not work for other kind of data, right? So the solution for this problem is instead of trying your model only on one particular train and test set, you can do a k-fold cross validation. So in the first fold, in the k-fold, what we are trying to do is to create k different fold. See, in the first fold we have 8 say our train data set has 3 oranges, 5 apple, and our test has 2 apple, right? In the next fold we will shuffle again everything, right? And we will create, say 10 fold means 10 times we are repeating this experiment, and the combination of train and test will differ. So maybe in one particular fold it can be 2 apple, but in some other fold it can be 2 orange also, and many other combinations it can be apple or orange. Then we will take the mean of all these experiments. So this is a better way of evaluating your model than evaluating your model on only one set of data, right? So it is always better to repeat the experiments multiple times. So this k-fold is a better method to evaluate your model if the number of samples are very less, right? So if the number of samples are less, do a k-fold. This is a mandatory. Otherwise there is always a chance that your model can be biased towards some particular test set. You may get good results in your lab, but if somebody else uses your model, the results may be very bad. Say in this case 2 apple, you will tell that my model is giving 100% accuracy, but somebody gives oranges in your test set, your performance of your model will not be good at all, right? So do a k-fold cross validation when the samples are very less. When you have millions of samples, you don't need to do it, because k-fold cross validation is very expensive. You have to repeat the experiments multiple times. Say if one experiment is taking 10 hours, doing a 10-fold cross validation, it will take 100 hours. You have to wait for a long time to complete your experiments. So this is expensive, it will take time, but when the number of samples are less, you should do a k-fold cross validation. But if you have a reasonable number of samples, or if you have a large number of samples, you don't need to do it. Whenever the sample size is less, this is a mandatory. You should do a k-fold cross validation. Data augmentation is required when you have less number of samples. So this is an artificial way of increasing the number of samples, right? You can apply for a particular class also. So you just assume that for class 1 you have 10 samples and class 2 you have 3 samples. So there is a data imbalance. So you can apply augmentation only to class 2 and you can make it as a 10. But the best way is to collect more samples, because augmentation will create transformed versions of whatever samples you have, right? So you're creating the transformed version, but if there is no way to collect more samples, then you can do data augmentation. Data augmentation will improve the performance to some extent, but it will not give you very high improvement, right? So this you should keep in mind. If you have less number of samples, do a k-fold cross validation. Okay, so we were discussing about linear and non-linear classifiers, right? Yeah. So yeah, with linear classifiers, see, the linear classifiers will not work these kind of cases. So if your data is linearly separable, then you can easily do with a linear classifier. You can use adaline or Perceptron models. But if the data is not linearly separable, say, you just assume that this is how the distribution of your samples look like. You cannot separate these two classes. The blue is one class and this red is the other class. You cannot separate these two classes with a line. You need a non-linear separation surface, right? So with linear classifiers, you cannot come with a non-linear separation surfaces. You have to create a non-linear classifier. So how can we create a non-linear classifier with a neural network? So if you want to create non-linear classifiers, then you have to use non-linear activation function. The purpose of activation function itself is to introduce non-linearity into the model, right? So instead of using a linear activation function, you can use a non-linear activation function. So what are the commonly used or popular non-linear activation functions? Are you aware about any non-linear activation functions? Sigmoid activation function, right? Okay, so we will see how can we use sigmoid in a neuron, right? So this is the this is how the sigmoid activation function look like. This is the definition of sigmoid, right? Y is equal to, this is how the sigmoid is defined. Y is equal to 1 divided by 1 plus e raised to minus x, where x is your input. And you can see that when x approaches minus infinity, what will be the value of y? 0. When x tends to minus infinity, y tends to 0. And when x tends to infinity, y tends to 1. So that means sigmoid is bounded. So you will get a value between 0 and 1, whatever be the value of x. Whatever be the value of x, output will be always between 0 and 1. This is good, right? Because if you look at adaline, it is not bounded. So again, doing classification with an identity function is very difficult. So we don't know where to put the threshold. But if it is between 0 and 1, you are getting a probability value. You can always set a threshold as 0.5. It is very easy, right? Because it is bounded. So if your model is giving, say, 0.7 as output, we can say that this is 1. Assume it is a binary classification. If your model is giving 0.7, we can consider this as class 1. If it is 0.3, we can consider this as class 0, right? So setting a threshold is very easy if it is between 0 and 1. So sigmoid is bounded and sigmoid is non-linear. You can look at the plot of sigmoid. See, this is a non-linear function. So sigmoid is non-linear, sigmoid is bounded, and if you want to use sigmoid with a gradient descent, what is the other criteria? Sigmoid should be differentiable. Sigmoid is differentiable. See, here you can see the derivative of sigmoid. If y is a sigmoid function, its derivative is y into 1 minus y. So sigmoid is a differentiable, right? Now I am going to put this sigmoid function as an activation function in the neuron. The same neuron that we discussed earlier. So this is a neuron that we discussed earlier, right? This one. Here we used identity function. I am going to replace identity function with a sigmoid function, right? So we have the sigmoid activation function here, right? So the only difference is the activation function. Everything else is same. So again, this neuron is taking two inputs, x1 and x2, and w1 and w2 are the weights associated with x1 and x2, right? So first we are computing this weighted sum, right? And so we want to find what values of x1, x2 and b minimizes the error, right? Correct, right? Oh, sorry, not x1, w1, w2 and b minimize. What value of w1, w2 and b minimizes the error, right? So again we can apply the gradient descent method. So new value of w1 we compute as w1 is equal to w1 minus alpha into dou e by dou w1. We will apply the derivative chain rule. So dou e by dou y, again it is this is again the same thing. The only difference is this part. Here we are taking the derivative of the sigmoid function. We will get y into 1 minus y. Everything else is same. So we will get a weight updation formula, right? So you can use this weight updation formula to update the weights in the case of a sigmoid neuron, right? So this is a non-linear neuron. So you can use, if you create a neural network with sigmoid neurons, then that will be a non-linear model, right? A non-linear. So the number of layers and neurons depends on the problem that you want to solve. If you want to come up with a very complex separation surface, then you need more such units, more sigmoid units, right? That is the complexity. So you can add any number of layers. Every layer you can have any number of neurons. But when you add more neurons and more layers, so in the end you are going to get a very complex non-linear architecture or non-linear network, right? Right. This is clear, right? See, other than neuron, other than this sigmoid, you can also use other activation functions. This I am going to skip. So here I am trying to use cross entropy instead of MSE. So if you use cross entropy, again you will get this weight updation formula. This I am skipping. So you can also use other activation functions. So if you look at the literature, you can see tanh, ReLU and all, right? All these activation functions are non-linear. You can use sigmoid, you can use tanh, ReLU, right? All these activation functions are non-linear. But see, if you look at the output of tanh, you will just compare sigmoid and a tanh. So you know that both sigmoid and tanh are differentiable. So you can also use tanh neurons instead of sigmoid neurons. The output of tanh is in the range -1 to 1, right? But sigmoid is in the range 0 to 1. And one advantage of tanh over sigmoid is, see, the derivative of tanh is higher than the derivative of sigmoid. So tanh neurons converge faster than sigmoid neurons, or tanh neurons are faster than sigmoid neurons. So if you design a neural network with tanh neurons, your model will converge much faster than sigmoid neurons. Now if you look at ReLU, see, ReLU is also non-linear, right? So the output of ReLU is in the range, what is output? 0 to infinity. So ReLU is not bounded, but tanh and sigmoid are bounded. ReLU is not bounded. But the derivative of ReLU is higher than the derivative of tanh. That means ReLU is faster than tanh. So if you look at the comparison of ReLU and tanh, you can see that ReLU is almost 6 times faster when compared to tanh. That means if your model with tanh is taking 6 hours to complete an experiment, with ReLU, this experiment will be over in 1 hour. And this is very important, right? Otherwise you have to wait. If your experiment is taking 6 months, with a TANH. In 1 month you can complete the experiment with a ReLU. So that is very important. But the disadvantage of ReLU is it is not bounded. So usually what people do is they use ReLU in the hidden layers. So in the hidden layers, and they use sigmoid in the output layer. The reason is we cannot use ReLU in the output layer because ReLU is not bounded. So we want a value between 0 and 1 as an output if it is a binary classifier, right? So if you use a sigmoid as an output, it is very easy to put the threshold. And hidden layer you can use a sigmoid, but that will make your model very slow. Because how we are updating the weights, W1 is equal to W1 minus alpha into dou E by dou W1. So when this derivative is very small, weight updation will be very slow, right? With the ReLU, weight updation will be much faster. Updating weights much faster means your model will learn much faster. So sigmoid neurons are will learn very slow, but ReLU neurons will learn faster, right? TANH you can use in the hidden layers, but once after the introduction of ReLU, almost all researchers, people use ReLU in the hidden layer. But the choice is yours. Even if you want to use sigmoid, you can use sigmoid, but you have to wait for a long time for your model to learn. The reason why people use ReLU is ReLU in the hidden layer is ReLU will learn faster. Is it clear? So you have some idea about different activation functions. All these activation functions, ReLU, TANH and sigmoid are a nonlinear activation function. We can design nonlinear classifiers using these activation functions. But you should also keep in mind that ReLU is not bounded. The other two are bounded, but ReLU is not bounded. But since we expect a probability value as an output, that is very easy for us to do this thresholding. So we use this sigmoid in the output layer, and all the hidden layers we use ReLU. Here you can see the plot of the derivatives. So these are the different activation functions. If you look at the derivative, you can see that the ReLU is having a higher derivative value. So if when your input is greater than 0, so the output will, the derivative will be very close to 1. It will be 1, right? Yeah. So till now what we discussed is a model with only one neuron. With one neuron you cannot create any complex model, right? See, our neuron can be a linear neuron or a non-linear neuron, but with one neuron you will not be able to solve a complex problem, right? So you have to create a neural network. A neural network is a network of neurons, right? So you will arrange neurons in this way in a layered fashion, where every layer you can have, say, n number of neurons. But this is again a hyperparameter. The number of layers, we don't know what combination will give you good result. So we always start with a simple neural network, and you can increase the complexity by adding more neurons to a layer or by adding more layers. So number of neurons in a layer and the number of layers are again hyperparameters, right? So here you can see an example of simple models and complex models. This is a single layer neural network, and yeah, you can see a neural network with 4 layers, right? You can increase the number of layers. So again, see, when you increase the number of layers or neurons, number of parameters will also increase. So the weight updation formula, see, you have to again come up with the weight updation formula. So in the case of a neural network, usually you have to apply this backpropagation algorithm. I am not going to discuss the backpropagation algorithm, but that is again the same. You have to find the derivatives with respect to every variables and you have to update it. So backpropagation I am not going to discuss because we don't have the time, but that is again the same. So we have to find the derivatives. So we want to find what values of these W's minimizes the error, and then you have to update it. Right. So in general, this is how this backpropagation work. So first you have to design a neural network, right? So the neural network can have a number of layers, and every layer you can have a number of neurons. So we have a neural network, we have the data. So we just assume that our neural network is a feed-forward neural network. So when we give the data to the neural network, it will give an output, right? So the predicted that is a predicted output. The predicted output you have to compare with the expected output. If the predicted output is not same as the expected output, then what is the next step? What does it mean? The parameters are not optimal. You have to update the parameters. So to update the parameters, you have to first you have to compute the error, and we want to take the we have to compute the partial derivatives, dou E by dou W1, W2, W3, all you have to compute the partial derivatives. That is what we do with back propagation. So and then you have to update the parameter. So W1 is equal to W1 minus alpha into dou E by dou W1, right? You update the parameter, and again you have to pass the input, and you have to compute the output and see whether there is an improvement, right? And if the predicted output is again not same as the expected output, you have to complete this process. So this is what happens with the learning, right? And after a certain number of iterations, your model will converge. So this is taken care by the gradient descent. When you have more number of variables, you are giving more workload to the gradient descent algorithm, right? If you have only 2 variables, gradient descent may converge very fast. But if you have 200 variables, gradient descent has to find what values of these 200 variables will give you the optimal result. When you have 2000 or 2 million variable, it will take more time, right? So gradient descent has to come up with optimal values for 2000 variables or 2 million variables. That will take time, right? It is not just the gradient descent, your memory requirement also will increase. You can imagine how much space is required to store a model with 2 million variables, right? So every variable is a floating point number, right? So memory requirement will also increase when you increase the number of parameters. In back propagation we are updating, we are finding the partial derivative. This is again the gradient descent only, right? So see the complexity, see when you select the model, you should be little bit careful. You should look at your data, the complexity and all those kind of things. So if the problem that you want to solve is simple, then even your model will work with a less amount of data, and you don't need to use a complex thing. But if the problem that you want to solve is very complex, say assume I want to differentiate between, say you take some simple example, so say a cat and the dog, and something like a what is it? Yeah, something that is very close. So if there is obvious differences between these two classes, then maybe with a less number of samples and a simple model will work. But when the features are very close to each other, then you may need more samples to train the model. This all depends on the complexity. Even when you do segmentation, see, segmenting some simple structures may be very easy. Segmenting the white matter and gray matter from the brain might not be that complex. But if you want to look for some kind of abnormalities in the brain, and that is very close to gray matter and all, you need a very complex model, right? So the complexity depends on of the model depends on the problem that you want to solve. But it is always better to start with a simple model, right? Okay, now we will see the limitations of artificial neural network. So here I am going to discuss a neural network to do this MNIST digit classification. So this is a very popular data set, right? So what we want to do is we want to classify the handwritten digits using a neural network, and I am going to do it with one neuron, and this is how the digits look like. So if you look at if you are familiar with this database, probably you will be knowing that the size of these images are 28 by 28. This is the size of your input image, and this input image you have to give to a neuron, and a neuron should say whether the input, the number that you gave is say 0, 1 or these 10 classes are there. We have 10 classes and our neural network should be able to classify this input number into 10 classes, right? So here I am using 10 neurons. I'm going to do this classification with a neural network with 1 layer and a 10 neurons. If the input is 0, this neuron will activate. If the input is 1, this neuron will activate and so on, right? So our input is an image. So since I cannot give the image as such to this neural network, what I am doing here is I am converting my image to a column vector. So the size of my image is 28 by 28 and I am going to convert this to a column vector. So when I convert this image to a column vector, I will get a column neurons, right? Our input image size is 28 by 28 and this neural network has 7,850 parameters, right? Now if I add number of layers, what will happen? Number of parameters will increase. Or if I increase the size of an image, instead of 28 by 28, if I use an image of size 2000 by 2000, you can imagine how many parameters will be there. This is the problem with a traditional neural network. So if you increase the complexity or if you increase the size of the image, the parameters will increase by a large extent. This is one problem in using ANNs for ANNs to work with images. The other problem is, if you want to work with ANN, you have to convert the image into a column vector. The problem with converting an image into a column vector is, when you convert an image into a column vector, you will lose the spatial relationship between the pixels. Because in the case of an image, there exists some kind of spatial relationship, right? That advantage you will lose when you convert the image to a column vector. The other one is the scalability. The scalability is an issue with ANN. If you scale your neural network, if you add more layers, more neurons, the number of parameters will increase by a large extent. So these are some of the issues in with ANN, right? So you can solve these problems of ANN with a convolution operator. So you can use a convolution operator in a neuron to make it a convolutional neural network. We will see how can we use a convolution operator, and we will see what are the advantages of using a convolution operator. Okay, this is clear, right? Any questions? Okay. So first we will see what is convolution, and then we will see how can we use convolution in a neural network. So convolution is a basic operation that can be used to extract information from images. So you can use convolution. So if you want to use convolution, see you need a kernel, and if you convolve an image or a signal with a kernel, you will get features, right? So we will do some simple experiment to see how can we extract features from the response as a linear combination of the neighboring pixel. So this operation is simple and straightforward. But once you do this convolution, you will be able to extract some features, right? So this is how it works. I don't have time to discuss it in detail, but you will get some idea with this picture. So I have an image and I have a kernel. So I have to place this kernel over these pixels in the image, and I have to compute a response. So I will place this kernel at this particular point, and I will compute the weighted sum. So how I compute the weighted sum? It is 0 into this 4 plus this 0 into this 0 plus this 0 into this 0 and so on, right? And this point will be replaced with the weighted sum. Then I will place this kernel at the next point, or what I do is I slide my kernel over the image, right? And I will compute the weighted sum. So the output that you are going to get is the response of a filter on an image, and that you can also call it as a feature vector. So if you use different kinds of kernels, you will get different responses. Right, we will do a simple experiment to see how a convolution work. Okay, I will do this experiment on this cameraman image. In MATLAB, you can read an image like this. So I am reading an image to the variable k. So this is my input image. So now I am going to do convolution. To do convolution, I need a kernel. I am going to create a simple kernel. So what this kernel will do? So what I did is I created a kernel of size 5 by 5, and what are those values? 1 by 25. Ones of 5 comma 5 dots 5. So if I convolve this image with this kernel, what will happen to the image? You know how to do the convolution, right? So you have to place this kernel on each and every point in the image, right? And then we are computing a response. How we are computing the response? The weighted sum. This is nothing but the weighted sum. So what this kernel will do? It replaces every pixel with the mean of the 5 by 5 neighborhood. It replaces every pixel with the mean of the 5 by 5 neighborhood, right? So what will happen if you do this operation? What will happen to the image? It will blur. Why it blur? We are replacing every pixel with the mean. So if you replace every pixel with the mean, that will blur the image. Why that will blur the image? Because it will destroy the edges. Mean operation will destroy the edges, and as a result, the image will get blurred, right? So I am going to do this convolution. So MATLAB has a built-in function to do this one. So I have an image k, and this is my kernel h. And when we do this convolution, see, you have to take care of the border pixels. So how can we do convolution on these border pixels? See, you just assume that we are using an image of size 10 by 10 and a kernel of size 3 by 3. So in the border pixels, it is difficult for us to do the convolution because there is nothing is defined beyond or after the boundary pixels. So one way is to ignore the border pixels, or you have to do a zero padding. So if you are ignoring the border pixels, then we call the convolution a valid convolution. Otherwise, we can do a zero padding, and we call the convolution same convolution. Assume our image, we have an image of size 10 by 10, and we have a kernel of size 3 by 3. If you do valid convolution, what will be the size of the resultant image? Your image size is 10 by 10, your kernel size is 3 by 3. So if you want to do, you have, right. So we have an image and we have a kernel. See, this is our kernel, right? And we have the image k. And you have to place the center of this kernel at this point and compute the response. Since we don't have any pixels here, we cannot compute the response here. We cannot compute the response in this particular row. We cannot compute the response on this column, right? We cannot compute the response on the last column and the last row. The first row, these two rows we cannot compute the response. These two columns we cannot compute the response, right? So how many rows and how many columns we have to ignore? Yeah, in this case, 2 rows and 2 columns, but this again depends on the kernel size. If you use, instead of 3 by 3, if you use a 5 by 5 kernel, then 4 rows and 4 columns you have to ignore. So if you convolve an image of size 10 by 10 with a kernel of size 3 by 3, what will be the response? What will be the size of the resultant image? So kernel size is 3 by 3, image size is 10 by 10. How many rows you have to eliminate? 8. 2 rows you have to avoid, 2 columns you have to avoid. So size of the resultant image will be 8 by 8. But if you want 10 by 10, then you have to do a 0 padding. In this case, you have to pad 2 rows, these 2 rows and two rows and 2 columns you have to pad with zeros. Then you will get an image of size 10 by 10. So here I am giving same convolution. So this will pad zeros and it will do it. So you can see the response here. See, this is the response, right? So you can compare these 2 images. So this was our original image, and this is the result after the convolution, right? So you can see that there is blurring. Now if I increase the size of the kernel, the blurring will also increase, right? So this is what convolution will do. Here I used an averaging kernel. Now I am going to use a different kernel. So if you change the filter coefficients or the filter size, then the response will also be different, right? So now I am going to create a different kernel. So I am going to, this is my kernel, h is equal to so you have any idea what this kernel will do? So any idea? This will not sharpen. So this will give both positive and negative values. We will take absolute value. This is out. Yeah, the horizontal edges. You will get edges. See the features. You will get, now you are getting a different feature, right? So if you use different kernels, you will get different kinds of features. So you can use convolution to extract features, right? This is clear, right? So you can use convolution to extract the features. Now we are going to put this convolution concept into a neuron. So you will see how that works. Oh, I closed the. So this is how it works. So this is my image, and I use some kernel, and I got something like this, right? So can you tell me the size of this kernel that I used here? 3 by 3, right? And I did a valid convolution. My image size is 5 by 5, and if you convolve this image with a kernel of size 3 by 3, you will get a feature map of size 3 by 3. So if your image size is 3 by 3 and the kernel size is 3 by 3, then what will be the output size? 1 by 1, right? Only 1 pixel. Yeah. So this is the response of this is output of convolution with mean filters of different size. So here I used a kernel of size 7 by 7, 15 by 15 and 41 by 41. You can see what happens to the output image. The blurring will increase, right? Okay. So this all will skip. Okay. So now you can see we are trying to put this convolution into a neuron. So this is the traditional neuron. I'm trying to differentiate between a traditional neuron and a convolutional neuron. So in traditional neuron, you know what is happening, right? So this neuron is taking 2 inputs associated with both inputs. Associated with these inputs, we have the weights. Then we compute the weighted sum, and the weighted sum is given to an activation function. Output of the activation function is the output of the neuron, right? And with this gradient descent method, we will try to find the optimal values of the parameters W1, W2 and B, right? These are the parameters in a traditional neuron. Now, here I have a convolution neuron. See, I am using a kernel inside this neuron, and here the kernel size that I am using is a 3 by 3 kernel. So I have an input here. So this neuron will take an input. Inside this neuron, I will do a convolution. X convolution H. H is my kernel. So when I convolve my image with a kernel, you will get another image as an output. This is a feature, and we are adding bias B to this one. This is just adding a constant to this matrix. Right. Here we are adding bias to the weighted sum. And so output is A, right? Here this A is a scalar value, but in this case my A is again a feature. This is called a feature, a matrix, right? So I will give this A to an activation function, and the output that I am going to get, this Y is again an activated feature map. So output will be an activated feature map. In this case, output will be a scalar value. See, the advantage in this case is, see, here I am taking this cat image as an input. I don't need to convert this cat to a column vector. But if you want this neuron to process this cat, I have to convert this cat to a column vector. So I will lose this spatial relationship, right? Other important thing is, see, here I am using a 3 by 3 kernel. You just assume that the size of my input is 100 by 100. I am using this cat image as an input, and the size of this image is 100 by 100. And we are using only one neuron. How many parameters will be there? Take the traditional neuron. I am giving an image of size 100 by 100 to my neuron. How many parameters will be there? 10,000? 10,000 plus 1. 10,001 parameters will be there. Now, with this convolution neuron, how many parameters will be there? In the convolution neuron, what are the parameters? There are no W's. What I have is only a kernel. So the size of my kernel is 3 by 3. So the filter coefficients are the parameters. With gradient descent, I am trying to find the filter coefficients. So the gradient descent has to come up with a appropriate filter that can extract the correct features to do the classification. Now I am using only one neuron. How many parameters will be there? For a 3 by 3 kernel, how many parameters are there? 9 parameter. 9 parameter plus bias. So my convolution neuron has 10 parameters. The other neuron has 10,001 parameter. You see the difference, right? Number of parameters are very less, right? But with one neuron you can extract only one feature. One neuron can extract only one feature, but with one neuron you cannot do much, because you cannot do a better classification. Even if you use 10 such neurons, 10 convolution neurons, how many parameters will be there? 90. Still the number of parameters are less, right? That is one advantage of convolutional neural networks. So you can reduce the number of parameters to a large extent. If you use 10 neurons, then you can extract 10 different features. If you use 100 neurons, you can extract 100 different features. So we use the gradient descent to find the optimal values of these filters. Usually what we do is we initialize these filters with random values. So we don't know if you initialize a filter with a random value, what feature it is going to extract, right? But in the end, when you start training your convolutional neural network, the gradient descent will try to find the correct values for filter coefficients. What all features are required to extract to differentiate between two different classes. If it is a cat and the dog, what features of cat and the dog is required to separate these two classes? That is the duty of the gradient descent method. What kernels you should use to separate between the cat and the dog, right? So we don't know what kernels, what all features are required. But when you train a convolutional neural network, the gradient descent will come up with appropriate kernels to extract the correct features that can be used to separate between the cat and the dog. I hope you got some idea. Yeah, if it is RGB, then your input has 3 channels, R, G and B. So you can apply the same channels to R, G or B. All the 3 channels separate channel. Or if you want to combine RGB, the information from R, G and B, even you can use a 3D channel. All the 3 layers. Yeah, that is up to you. Bias is a constant, a single value. It is not a matrix. Yeah, that is added to all the values of the matrix. Yeah. Same value. If it is a 10, the 10 will be added to all the elements, all the matrix values. Then this is given to the activation function. So we'll get an activated feature map. So it looks something like this. See. Yes, the matrix is given to the activation function. It looks something like this. See, assume this is our input image, and when we do a convolution, we will get another matrix, right? So this is the convolved feature map, right? Then we will add a bias to this convolved feature map. So bias will not change the shape of your convolved feature map. You are adding a constant to every elements, right? And this is given to an activation function. So we'll get an activated feature map. Again, the size will be same. It will not change the dimension. And this is given to the neurons in the next layer. But usually we do something called the pooling to reduce the size of the feature map. So this is how it works. And we use the parameters in this case is the kernel, the filter coefficients, right? And why we do this pooling, you have any idea? You can see this pooling in convolutional neural network, right? Assume that your input image is of size, say, 100 by 100, and if you use 10 kernels, right, or 10 neurons, every neuron we will get a feature map of size 100 by 100. So if you use 10 such neurons, the size of our feature map will be 100 by 100 by 10. If you use 100 neurons, it will be 100 by 100 by 100. So you need a large amount of memory to store the feature map, right? So this sometimes can create problem. So what you can do is you can reduce the size of the feature map with the help of another technique called pooling. So this is how pooling work. So either you can use a max pooling or average pooling. So if you are using a max pooling with a filter of size 2 by 2, then see we are using a stride 2. So 2 by 2 means you will take a 2 by 2 region and find the maximum value. So in this case the maximum value is 6, and since we are using a stride of 2, we will skip every alternate row and column, and we will take the maximum value from this 2 by 2 region. So that is 8. And then we will skip this row and we will come here. The maximum value here is 3, maximum value here is 4. So if you use a pooled filter of size 2 by 2 with a stride 2, you can reduce the size of the feature map of size 4 by 4 to 2 by 2, right? But here we are throwing away some of the features, but still we are preserving the most important features. That is what we do with the max pooling. And with other commonly used pooling technique is average pooling. In average pooling, what we do is instead of taking the maximum value, we will take the average value. So we are taking this is the average feature value. But most commonly people use maximum value. So we are keeping the most important features. And another advantage of pooling is it can also average pooling, you are taking an average of all those feature values. can take average. What is the problem taking average? Because all these variables are again floating point variables, right? No, binary is in the end only. In the end, we are doing converting something to say some class value, but it can be even if you take if you replace everything with the average, still it is fine. What is the whether I yeah, sigmoid you can give a floating point value also as an input. The output will be an activated feature map. So if you give when you give something to sigmoid, it can be floating point or integer. It doesn't matter, right? Right. So another advantage of pooling is see pooling is invariant to small transformations in your image. If a small rotation or small translation, so this will not make much change with pooling. And pooling with if you use pooling to some extent you can avoid overfitting also. Because of this reason, this is another advantage of using pooling. Of course, you can reduce the size of your feature vector. The memory requirement can be, it is not the memory requirement. See, if you give the original size feature vector to the next layer, then the number of operations that you do for convolution will be more. You just assume that your feature vector size is 100 by 100 and your kernel size is 3 by 3. So how many multiplications you have to do this convolution? You have an image of size 100 by 100 and you have a kernel of size 3 by 3. So total how many multiplications you have to do? 100 by 100 into 3 by 3. This many multiplications you have to do. So if this 100 by 100 feature vector, if you can make it a 50 by 50 feature vector, then the number of multiplications that you have to do can be it will be much lesser. So the total number of multiplications can be significantly reduced with the help of pooling. Okay, so usually this is how a convolutional neural network look like. So we have an input. We just assume that our input image is of size 28 by 28, and here I am using 3 kernels. 3 kernels means 3 neurons, right? With the 3 neurons, assume that so after the first convolutional layer, I got a feature map of size 24 by 24 by 3. Can you tell me the size of the kernel that I used in this layer? I used 3 kernels. That is why I got 3 feature map. This is the feature map that I got. So the feature map size is 24 by 24. The image size was 28 by 28. What is the kernel size? 5 by 5, right? 5 by 5. Because 2 rows up, 2 rows down, 2 columns left, 2 columns right, right? So I used 3 convolutional neurons, or you can say 3 kernels with the kernel size 5 by 5. So I will get a feature map of size 24 by 24 by 3 as output. I will give this to activation function. I will get an activated feature map of size 24 by 24 by 3. This before giving to the next convolutional layer, what I do is I will do a pooling to reduce the size of the feature map. This is to reduce the number of multiplications, right? So the output becomes 12 by 12 by 3. This I will give to the next layer. So here in this case, I am giving this to a fully connected layer because I am creating a neural network with only one convolutional layer. So the last layer is usually, when we do classification, usually the last layer is a fully connected layer. Because now what happens is in this fully connected layer, all these pixels, you have to convert to a column vector and you can connect to every neurons. Because we want to do a classification. Usually the last layer is a fully connected layer if you want to do a classification. All the the other hidden layers, we use convolutional layers. So these all are convolutional neurons And in the last layer we use the traditional neurons because we want to do a classification. Otherwise, the output of a convolutional neuron is a vector, but we need a scalar value, right, in the end. So, in the last layer we use sigmoid neurons, the normal sigmoid neurons, and all the hidden layers, the convolutional layers are convolutional neurons. So, this is how we design a convolutional neural network. Got it? Yeah, this one. Yeah, you can assume it in this way. So first neuron is connected to 12 by 12 by 3 neurons, 12 by 12 by 3 values. Second neuron, so this neuron has a 12 by 12 by 3 connections. This neuron is also having 12 by 12 by 3 connections. So that is why this is called a fully connected layer. Every neuron in this layer is connected to every pixel in this one. Either you can arrange it in a column way and connect everything, or if you make it in a column wise, so layer by layer, every layer, first layer, second layer, third layer. That order doesn't matter much, but in every frameworks there may be a standard way of doing it. It will be the first layer followed by second layer followed by, this can again row major form or column major form, but that depends on the framework that you are using. Okay, so this is how we design a convolutional neural network to do image classification. And now we will come to the old question. See, why deep learning performs better than the traditional machine learning approaches. This is what we discussed in the beginning, right? In the case of traditional machine learning, you have to give features. So you need the help of assume we want to identify whether the input object is a car or a bike. So we need the help of an expert to find the features of a car and the features of bike, right? So an expert will identify what are the features of car that can be used to differentiate it from a bike, right? Based on that features, we will design a model. Here we can use a traditional machine learning algorithm, we will get an output. So we don't need this person here. Who will do this person's work? Who will do this person's work? Convolution will do. Convolution will do with the help of kernel, right? So here we don't need a manual feature extraction. You just need to give the images, right? And your optimization algorithm will come up with the appropriate kernel values to find the correct features to do the classification. This is how the convolutional neural network work. That actually convolutional neural network made all those PhD students very lazy. They don't have any work, right? Data is there, model is there, just to do some experiments. Most of our students are not designing any new architectures. They are using existing architecture to solve the problems, right? As a computer science person or a computer science student, we have to come up with a efficient architectures. It is not using some of the existing architecture to solve our problem, right? We should try to develop more efficient architectures, right? I hope you got some idea about convolutional neural network. There are some more slides, but I don't have time to explain those things. Actually, I thought of discussing few architectures like AlexNet and VGG, but we don't have time. Maybe I can just show some of the works that we are doing in our lab. That may be more interesting to you. At NITK, I'm heading a lab called Vision and Image Processing Lab. So my lab has around 35 students, around 5 or 6 PhD students, and the rest are MTech and BTech students. And we have collaborations with different hospitals and other research centers. And usually we work with medical images. So we develop automated methods to analyze medical images. So we do both classification, segmentation and all. So these are some of the projects that we did recently. So we developed efficient methods for image denoising. Image denoising means reducing the amount of noise from an image. So if your image has noise, then it becomes very difficult for an expert to analyze the image. So this noise can hide important image features. This is same for automated methods also. So if your automated methods if a convolutional neural network wants to extract the features, you have to make sure that the image is a clean image. In the presence of noise, the CNN methods may not be able to extract the features properly. So we developed a large number of denoising methods to clean medical images, because one algorithm might not work with the different imaging modalities. That is because different imaging modalities may introduce different kinds of noise. If you look at MRI, the kind of noise is rise noise, or if the MRI is occurred with multi-coils, then the noise may follow a non-central chi-distributed. Or in some other kind of images, the noise can be Gaussian, right? So in ultrasound, the noise is speckled. So one particular algorithm will not take care of different kinds of noise. We should study what is the type of noise in an image, and accordingly we should develop the denoising method. So we developed denoising methods for different kinds of medical images. So this is a project that we did recently. This project is to extract the blood vessels from these fundus photographs. And this is a project that we did with Sri Chitradirunal Institute of Medical Sciences and Technology. So this project was to identify the type of stroke. Basically, the stroke can be ischemic or hemorrhagic. So if you give an image, this non-contrast CT image, because this model take NCCT image as an input, and the model will tell whether this image is of a patient with a stroke or not. And if this is an image of a patient with a stroke, then it will also tell what is the type of stroke, whether the stroke is ischemic or hemorrhagic. If the stroke is ischemic, the model will find what is the true extent of stroke, and if it is hemorrhagic, then it will find what type of hemorrhage is it, because there are different, basically this hemorrhage stroke can be of 5 types or something like that. So this is what this model will do. So this is another work that we did with a hospital in Jaipur. So this project is to find this cyst in the retina. So the input to this model is OCT image. So with OCT image, you can image the retina. You will get the cross sections of the retina. And if there is a cyst, so usually what the doctors do is they will inject a medicine called anti-VEGF to this to treat this cyst, and the amount of this injection depends on the volume of cyst. So manually finding the cystic volume is a time-consuming task. So a retina surgeon has to go through all these images. This is a 3D image. So the surgeon has to go through all those cross sections, and then he has to compute the volume. So this is a time-consuming task. So with the model that we developed, so it will take a fraction of seconds to find the cystic volume. So the model will find where is the cyst and what is the volume. So this is a project that we did recently. This project is about a semi-supervised medical image segmentation. So probably you will be familiar with fully supervised models, right? So see, these machine learning techniques can be supervised or unsupervised, right? Supervised means you have to give the labels, right? Without labels, it will not work, right? So supervision is with the help of labels. But the problem with the supervised models is the labels itself. So the problem is you have to prepare the ground truth, right? If I want to work with a doctor on something related to stroke, see, the doctor has to sit and find whether these images belongs to stroke or not, or if it is a retinal cyst, the doctor has to create the labels for me. And if the doctor is busy, most of the time the doctors will be busy, so they cannot spend a large amount of time to label it. this usually happens with us. We collaborate with the different hospitals, and the problem is they will tell us that if you need 10 images, I can do it, but if you need 10,000, it's very difficult. Right. So what we do is I will send my PhD student. My PhD student will sit with some students of the doctors, and they will prepare the labeled data set. But this is very difficult. So the other solution is to use semi-supervised methods. In semi-supervised methods, the advantage is you can make use of both labeled and unlabeled data. Every hospitals will have data, but this data may not be labeled. I don't need thousands of labeled data. If the doctor can label 100 samples, other 900 probably will not be labeled. So my model can work with 100 labeled and 900 unlabeled. That is how the semi-supervised methods work. But if you use fully supervised, you can use only these 100 labels. Other 900 you cannot use because it is not labeled. So we developed at least say some 4 or 5 unsupervised, semi-supervised techniques, and these techniques are giving very good results when compared to the state of the art. So this is another project that we did recently. This is for segmenting ribs from this X-ray. And segmenting ribs also has certain advantages. So see, small fractures and all you cannot easily see in this chest X-ray images. So once you segment this rib, you can see those small fractures much clearly. So this is another project that we did with Srijit Renal Institute of Medical Sciences and Technology. This project is related to cortical dysplasia. Cortical dysplasia is a kind of abnormality in the brain that can lead to epilepsy. So if the epilepsy can happen because of multiple reasons, but if the epilepsy is because of cortical dysplasia, then the only solution is surgery. And to do, when we do surgery, they have to make sure that they remove the this cortical dysplasia region completely, otherwise it can recur again. But identifying this cortical dysplasia region from the FLAIR MRI images is not that easy, because these cortical dysplasia regions and gray matter regions are having more or less the same intensity. Especially in the preliminary stage, it is very difficult to do it. So we developed a model that can automatically differentiate between this gray matter region and cortical dysplasia regions. So yeah, I added some other slides. So this is a project related to denoising. So you can see, this is again OCT images. This is how the OCT images, input images look like. After denoising, it looks something like this. Yeah. No, it will not blur. So not all methods will blur. So when you do this denoising, you have to make sure that the simple averaging will blur. But you have to make sure that the denoising method will not destroy the edges. Edge preserved denoising methods you should use. There exist many such methods called non-local means and all. Even with this is a method with a convolutional neural net, autoencodates. And this is a project that we did recently with KMC. So this model, this project is to identify the molecular typing of breast cancer. The default treatment is chemotherapy, right? Chemotherapy may not be a correct choice for all subtypes of cancer. So see, for some subtypes of cancer, maybe a hormone therapy may be better for better than chemotherapy. But identifying the subtype is not that easy. So manually, a pathologist has to look at all these images with the different biomarkers, and the pathologist has to find what is a subtype. So we automated this process with the help of a convolutional neural network. So our model will take all these 4 biomarkers, and then it will tell what is the subtype of the cancer. So these are some of the works that we did in our lab. So yeah, so we have collaborations with many hospitals in the southern part of India. We are working with Srijit Rajan, AMC, JSS, CMC Vellore, and all. So we have multiple projects, and if anybody is interested in collaborating with us, you are always welcome. I hope you got some idea about neural networks and CNNs, right? Because in 3 hours it is very difficult to explain the whole concept, right? Okay, so thank you for attending this talk. And if you have any questions, you can ask me, or you can always you can mail me, jenyrajan@nitk.edu.in if you want to discuss something. Okay. Thank you.
I would like to thank Dr. Jeny Rajan sir for his informative session on deep learning techniques. We got in-depth knowledge about working of deep learning algorithms. Thank you, sir. Now I request Professor A.M. Khan, Department of Electronics, Mangalore University, to present a small token of appreciation to Dr. Jeny Rajan sir on behalf of Department of Computer Science, Mangalore University and AICTE et al.